Welcome to our meetup, which is the first one for Codebeez, and I don't know how many one for DataWorks. They were so nice to co-host this with us, so we can.
And how to increment over columns and over rows, and we do fast computations on those. So what we in general can say, it's not always true, but in general we can say that a pandas data frame is built out of different NumPy arrays. So that's a bit of under the hood of a pandas data frame. Well, what is an orca? Well, we also have a Spark data frame. Sort of a heavy weight. If you have large amount of data, you need something to attack the data and just be able to handle that. That's the orca. So we have indeed also heterogeneous columns that we are lazy. But the orca mainly becomes useful at scale. And what we saw with pandas is when we cannot fit the data in memory, then we can start thinking about using something like a Spark data frame. Well, one observation is that in all these libraries and these different languages, because Spark is basically built on Scala, it's a JVM toolchain, they all represent data in data frames for data science purposes. So the data frame is now extending across languages. R had it for a long time, now Python has it, now we have it in Spark. Well, if we look at the under the hood of a Spark data frame, we go insane, right? Instead of saying, oh, we just have a few types and we have NumPy arrays, we have this almost like a compiler structure where we have the front end, sort of the middle end, and the back end. What we can say, for instance, is that we have on the front end, well, we have some SQL statements, for instance. There's different. We can actually turn panda in an orca. So we have panda. We add a wheel. Out comes the orca. Black and not much gray area there. And there's actually a one-liner to do it. We have this panda data frame, DF. You just put it into create data frame of the Spark system, Spark context, look, comes an orca. So what does this mean? What does this mean? We can also turn an orca into a panda. So we have an orca, we subtract the wheel, out comes the panda. So we have on a Spark data frame, we have a method called toPandas. You can call that out comes a pandas data frame. And I've seen quite some uses for this. So for instance, this is quite common. If you did a select statement in SQL on your big data, you go from data to information and you make a select. That information is probably an order less in size than the original data set or more. And it could fit in memory. So you could at that stage go to a pandas data frame and rely on your toolchain in pandas, NumPy, SciPy, scikit-learn to fit data, to do the exploration. So I see this a lot. The other one, yeah, we also see this, but I'll show you a bit later when we come to a little bit in the context of unit testing. Okay. Well, under the hood, PyArrow does this magic between transforming phenotypes. So PyArrow is a universal data memory format optimized for analytical computing. Well, if you did a little bit of that, you'll notice that you do a lot of selections on columns and less so on rows. Columns are where one type of data, for instance a metric, distance or age, is organized, and the rows are mostly the samples. So we are mostly interested if we want to take a mean of age, the average age, it's column based. So it includes a communication protocol. So it has, it's on the next slide, but it has some kind of a server client mechanism. which supports a zero copy. Let me just make some. Because you can imagine if on the top picture we have pandas, Spark, but we could also have Parquet, HBase. We have this this data frame. This data frame that we want to use in all these contexts. Well, we are constantly copying data and converting to a different format. And that's usually inefficient. So what PyArrow wants to do is to sit in the middle as a sort of common backend, where we can say two pandas or create data frame and put in a panda and stream our, let's say stream our data, these tuples, instead of copying stuff and converting it to different formats. So in the end, we want less overhead of these conversions. Questions so far? We got one, yeah.
What's a whale?
What's a whale? Now the whale is the big data, it's the scale. So if I have a orca, I take away the scale, I have a pond. Yeah, good question. Yeah, one?
Yeah, is PyArrow actually already used within Spark? I thought that was still ongoing.
No, it's used, yeah. I think Spark 2.3.
Okay.
So it's been almost 2 years now.
Oh.
Yeah. And it made a huge increase of speed in doing these conversions. But we can also now do user-defined function, so a Python function. And we can apply it to a whole column in terms of a pandas call. And then the result is sent back as a Spark call.
Is Spark, is it a Python framework here or an adapter to the Alpha?
Yeah, it's an adapter in the sense that Python is almost never used to actually implement any kind of real compute.
Yeah.
It's mainly to interface with computing systems. So TensorFlow, pandas itself is a lot of C, or at least compiled variants of Python. And Spark is mostly Scala. Okay, so this is a little bit how that looks. We have the Spark SQL. We can say to arrow. Hey, that's
Thumbs up.
Someone at the door, you didn't make a mistake or something.
So what happens is we actually stream batches of rows. So remember, we are focusing on columns, but we are streaming like any 100 rows, and then the next 100 rows. And there's some kind of a nice vision on that. If you stream on rows, you can just transpose it, and then you can concatenate. I don't have that here in the slides, but it's kind of elegantly how PyArrow is designed. But just remember, when we stream PyArrow, we stream batches of rows. So we go from the cluster, for instance, to the PySpark worker, or in this case, element. Could be the driver. So we go from the worker on the left to the driver, and we go from the Spark data frame to the pandas data frame. And then again, we can do the same in the other direction. And this socket, the streaming, will allow us to get the data which we want and not be overly copying and converting. Okay, so pandas, koalas. Pandas and orcas is now clear, I hope. But koalas.
You lose that whole benefit of getting the entire graph, get it optimized.
Yeah.
And your code might be a lot less performant.
Yes, that's a good question. And one of the design principles is that only the aggregates will resolve to pandas. And I think in practice there should be somewhere a switch where you can say, I don't want to resolve as pandas, but I want to keep it as Spark. But, I think some simple statements as selecting columns will still return Spark data.
Okay.
It's only when you do aggregate and
So under the hood, what's the difference? Does the koalas, if you have the koalas unit test, does it do all the or most of these things as well?
yeah, it actually does these conversions under the hood. Because it is an abstracting layer on top of these two systems, and you won't really notice when you're transitioning. you will notice when the return result is concrete instead of lazy. That's the main thing you will notice. Yeah. Okay. So to summarize, yeah, we got one. Yeah.
Can you tell a bit more about what Orca brings more than what PySpark can bring? Is it only just the interop between pandas and similar data frames, or?
I mean, the whole. I introduced Orca myself. It's my invention.
Oh, I'm sorry.
I just needed an animal that could say.
I don't know.
I mean, if you,
maybe it was a picture.
I mean, if you take a panda and you add the big scale reel, for me, you get an orca.
Okay, that was fair enough.
I mean, there's another package that does the same as koalas. Got the name, something like Oberton or something, a bit more abstract. But they wanted to achieve the same result. Okay, to summarize, Python is animal friendly, but with Codebeez we have another animal on the scene. Okay? So just waiting for the next package. Orca could be something we could invent in-house.
But if you have koalas, why would you?
Koalas might actually be useful. That's sort of the result. I did talk to the koalas developers at Spark Summit, and there's only 4 guys. I mean, if we are going to develop our systems into koalas, which is an API delivered by Databricks, I'm not so sure about it yet. I mean, PySpark is here to stay, pandas are here to stay, koalas. We want to actually trust your systems on.
Yeah, especially with the bushfires in Australia.
Bushfires.
Too soon.
Yeah, if you go through your life cycle and you hit the wall of legacy code and your code is on fire, you might actually prefer an orca. So, team membership influences your choices. I mean, half of my previous team was comfortable with Spark, half of it was not. But in the end, they had to learn to do also their exploration in Spark. So you can take that line, but if you just hire some data scientists and want to have results, I think they will prefer working with pandas. So team membership influences the choice of API, but also the where you are in the life cycle of the product. So my final slide is the elephant in the room. Python, of course, and thank you. I know I had a lot of questions, but if there are any questions, there's some time. Yeah?
So I didn't get how PyArrow took care of not copying so much.
Yeah, so that's a good question. When you do 2 pandas, for instance, you do it on mostly you do it on a subset of your master data. Okay? You only want these columns and these rows. And that data is then streamed in batches of rows to the other interface, the other system. So that's about it. You're not streaming your whole big data. You're streaming a subselect that you want to represent in another system, and you're streaming it in batches, and then the system, the client on the other side needs to process it.
So when would you copy the whole batch? Because that's impossible, right? The whole point is that's not possible.
I mean, there are limits. I think by default on Spark we have a result size limit of 1 gigabyte. So yeah, you can actually pump, if you have 5 workers, you can pump 5 gigabytes into your driver.
Yeah.
And it might have 5 gigabytes of spare memory, but that's about the limit, I would say. Nothing more than a few gigabytes. Yeah. Other questions? Then I want to thank you, and I think we'll have a small break, get some cold pizza. And
So, let's go. My name is Laurens Koppenol. It's very nice to be here as a guest from DataWorks on the Codebeez Meetup. I'm really interested in what kind of crowd we have here today. Who's a developer? Who's a data scientist? Few. Data engineer? More? Do we have something else? Consultant. Designer? Yeah?
No, consultant.
Yeah, you?
Physicist?
Physicist? Nice. Yes?
Geophysicist?
Geophysicist. Is there a battle here?
Yes.
I want someone to raise their hand and say exogeophysicist.
Okay. Which one of you likes to play games? I see a lot of hands, so this is nice. Because let's see if this works. The topic of today is not working. How to build a game and not play it. So sorry to disappoint 95% of the crowd who just raised their hand. We're not going to play a game. No, we will play a game. It's okay. We will play a game. This is the game we're talking about tonight. As you can see, it's a weird kind of car. Because it's not a car, it's a train. It's about racing trains, and I'll show you why. Because I started off as I studied here in Utrecht, artificial intelligence. Just like it's nice that a few study mates showed up here, which I haven't seen for a few years. So this is good timing. I did a data science traineeship at Xomnia. I worked for 3.5 years as a data scientist for the Dutch rail infrastructure company, ProRail. And that's also where I made this game as sort of workshop material to have people play around with AI and just to get familiar with it as a use case. And nowadays I'm data engineer, scientist, mostly scientist at DataWorks, currently employed at Port of Rotterdam. There I'm an engineer, but machine learning engineer. It's like fluid work. So tonight we have two parts. First we'll talk about building the game, which is I think interesting for developers, but it's a funny little game. So it's not like we're going talk about 1 hour of how to implement the game. It's in large outlines. So this is what the game is about. This is how it works, and then we'll focus on the most fun part. I think then we'll not play the game, but we'll still look at the game being played. So let's start with part 1, building the game. And I need a volunteer. I need a volunteer because we're gonna start with just playing the game. Let's see if it works.
Is the volunteer here?
Pick me.
Yeah, come over. So, go ahead. Here's the computer. Yeah,
Right.
the screen is over there, so it's a little bit tough. This
What
is
do we
challenge.
Are you using me for?
Yeah, this is good. Okay, you crashed. Anyone else want to try? Someone who thinks who can beat him?
He's teaching the game on us, man.
Who?
That's evil.
Who has had more beer than him?
Do you have a joystick?
Steering wheel. The training information out plus. That's you. I'm feeling amazing. Good driving.
Nice. Okay, so the two guys who just played the game, can you explain how the game works?
Yeah, sure. So basically you use the arrows. If you press forward, it's going to keep having speed. If you go backwards, it kind of goes backwards, although I suspect it to go this way and not the other way around, but that's fine, implementation details. You have the arrows to move the car to the train to the right and left, and then you just have to complete the maze, I guess.
Yeah. It's just like a normal train, right?
Yeah, sure. No rails, but that's fine.
So
Yeah.
GTA 2 controls, I guess.
Yeah, there you go.
Yeah, like you do.
But you don't get out
Yeah.
of the
Yeah. Anything to add?
train.
There's a very fast acceleration.
Yeah. Just like a normal train. Yeah. So that's the game, and it looks really fancy, of course. But what we're playing under the hood, not working at all, is this game. So this is basically the essence of the game. Is that we have a starting position, we have some track, we have to stay within the black area, otherwise we crash, as we just saw in 2 cases. And once we hit the blue area, we finished. There is a boundary here, which you could not see in the previous, like in the graphical track, because otherwise you could just reverse and then finish. So this is a super simple racing game. You use the 4 arrows to accelerate, decelerate. You cannot go backwards, but you can get back to 0 acceleration, 0 speed. And actually this image you see here is used for the game itself, because it will just interpret the colors, and that will say these are the boundaries of the game. So if you want to make a new map, a new track for the racing game, then you can just open up Paint and you can draw a new map. That I just did for myself because it's more fun to make a map like this than to use something else, I think. So that's basically the game. And I think, yeah.
What's the collision? Where's the collision happening? Because when you were drawing, you had a full-blown train or car, right?
Yeah.
But I only see a dot there. So
yeah, you were just a dot.
Kind of hack.
You were just a dot. Yeah, so you can actually move the train. You can overlap it a little bit with the curves. But also,
right.
Because this.
And cut the corner a little bit.
Yeah, you can cut the corners. Sometimes you can, sometimes you cannot. Depends on
where the middle is of the train.
Yeah, exactly. Yeah, and because the graphical overlay here, the edges here are not very clear because you have like the red-white area, and yeah, will you crash there? Will you not crash there? The answer is probably yes, but maybe not.
Hopefully not.
Yeah. So
no pit stops. No pit stops.
No, but you also don't run out of fuel. So it's okay. You can stay for quite a while. You can just move around the circle. It's okay.
How did you get from this one to, or from your Paint version to this one, or?
Yeah, actually what I did, I use a super cool program called Paint.net, which is like Paint, but then it also has the magic selector, like the magic wand from Photoshop. And I just selected all the grayish stuff, and I just made it black. Yeah. So it took me about 5 minutes to make the map, and I had to think more about like where to draw the line for the finish, so the people don't reverse, or the stuff we're going in later will not reverse, and just try to finish that way. Yeah. There was a question, yeah?
Well, once you're finished, you again have the red the border, so it's only 1 lap you can do. Or
Yeah, you can only do 1 lap, and once you crash or if you hit the finish, the game will just shut down because it says, okay, you've tried, and yeah.
So I noticed that the blue area is a bit large.
Yes.
I guess that's because
Yes.
you only point-wise sample whether you have died or won or if you're still okay.
Yeah.
And the black or the red boundary to prevent people from reversing into the goal was quite small. Can you?
Yes. Oh, we can try it later.
Can you go
We'll try it
that
after-
fast?
We'll try it after presentation. I'm happy you did not follow me. And that's a very good one, and it also touches the next point, because to make a game like this, so we have the map. We know the mechanics. We can race around and we can hit stuff and we can finish. But to actually make the train or the car move, it has to listen to input and it has to do something. And it doesn't look like we perceive what could this entity, this egg that we really tried to push out and finally came out, what can it perceive?
It's maybe the distance to the wall.
Distance from the wall?
From the central point.
Yeah, good one.
And use that as like a cost function, like if you try to maximize or something.
Yeah, good one. What else could we perceive?
Distance from your previous location.
Distance from previous location, yeah. So that could also be speed. It's like the current speed. Yeah. What else?
Perhaps probability of collision?
Probability of collision, yeah. And that would be something something calculated from something you see, right?
Yeah.
And what do we have to see? Again, maybe distance to the wall.
Velocity?
Velocity, distance to the wall. Yeah.
Direction.
Direction. So I'll put the previous thing back on. and now you also see why it was stuck, right?
Yes.
These things are coming out of the air.
Nightmare.
So, does this make something intelligent if we do it like this? Do we have an intelligent egg?
Depends on the question mark, right?
Yeah, it really depends on the question mark. So the implementation we just saw is basically a puppet. So it just tells us that we are the puppet master, and instead of controlling it during the game, by pressing the buttons, we control it before the game. We just say, okay, these are your rules, these are your strings, my puppet, go, and then it will reach the finish. So it's not bad, but it's not intelligent. So. How could we make this faster? How could we make it better? How can we improve? Well, we're doing, right? So we can, it's like, if we want to improve, we probably want to improve its speed because it already reached the finish. So maybe we want to increase the comfort level of the people inside the train. So maybe stop shaking.
Would be nice.
Yeah, it would be nice, yeah. And or we could increase the speed, but if we stop shaking, maybe we already reach the finish sooner. So what we could do, so if we want to evaluate what we currently did, so we could say, okay, we're just going to add more of these eggs and just have them all try to reach the finish. Like, oh, maybe let's see where they go. Now it looks more like a train, right? There we go. Yeah. But these things all have the same behavior because they just check left, right, and they just go for the finish. So they should end up all in the same spot.
Yes.
Yeah. And then we're done because they have exactly the same behavior. So if we would say, currently it has two rules. It has one rule saying go right if you shouldn't go left, and go left if you shouldn't go right. So there's hardly anything to tweak there. So if we just say, okay, and then if we would say we're going to take the top 20% from the population becomes a lot smaller. So we have to fill the population up again, because if we would say we take the top 20% and we're just going to run it again, then we would get the same scores again because their behavior did not change. So we can fill it up again, and we can fill it up by taking the top 20%, for example, and making small mutations to it. So they were initially randomly, they had random weights in the neural net, so they had more or less random behavior within certain boundaries, and we can say, hey, we're going to change your weights a little bit, and then just try it again. But we could also keep that 20% and just fill the rest up with mutations. So we would get a sort of loop like this. So we initialize the first generation, the first 100 or the first 1,000 would be the first generation. They all try to race to the finish. Then we say, okay, 20% of you scored pretty well, or like the better part has a higher chance of being selected. So we have the evaluation and the selection. And then we apply some operators to go from the smaller group of selected trains we had to go back to the larger group of selected trains. So we are back at 100% population size. And then, so that's the operators application and the reinsertion. And we could say higher fitness, the more chance to be selected. On two of them. And then it will mutate and a few of them and start random bots as well.
I think it's fun with it.
I like the green clouds. Is this AI?
Yeah.
This is what peak performance is.
So it could be stuck on this for a little while. But are there questions?
Well, can you maybe show the gradient again that you drew?
Yeah.
Of the
Oh, stop.
It's going faster and faster.
Yeah, because it knows where to go.
Yeah, so this is actually quite interesting, right? Because you already.
This is my corner.
Okay, it's going to be. We know how to do it.
Yeah.
But you already, at any point in the game, you can already give immediate feedback to the agent and how well it's doing. Right? It's quite often in games, say in chat
for example, you can really know how you did it at the very end.
Yeah.
Right? Did you win or did you lose or did you play a draw?
Yeah.
So that's also, what would happen, do you think, if you would remove the gradient and would only tell it in the end, you have 100 points?
Yeah, now, because it only sees the track via the sensor this has, it doesn't know the gradient. So it only knows the distance to the walls, like it has 5 sensors, one straight ahead, 30, minus 30, 60, minus 60 gradient degrees. But if you would, you could also give it the gradient of the 3 by 3 pixels around it, for example, and it can use that information to direct itself. And then it just use, and you can also give it feedback during, but then it opens up options for other algorithms as well. Yeah, so there are many options there. Yeah.
So the inputs are all the sensors.
Yeah.
And the output is one of 5 actions. What was it again?
It has 2 actions as outputs, and that is a degree whether it should sub between steering left and steering right, and between accelerating and decelerating. So it has 5 inputs, 2 outputs. Yeah, yeah. So here it has an advantage over a human player because a human can just press the button. It's a 1 or a 0, and this one can accelerate at half speed, for example. Yeah. Also increasing the action pace and making it a little bit harder for the player.
But what is the mutation then that it's doing?
It has it performs a small change in all the weights of the neural net.
But the neural net has as input the values of the 4 sensors.
Yes.
And the output is 1 value? Or?
2 values: the rotation and the acceleration. Yeah. Yeah.
Oh yeah, what it should do, the action.
Yeah, those are the action. The output is the action.
And how do you decide on, it's the random debate?
Yeah, it starts random. Yeah.
But if the mutation is a random.
Yeah, the mutation is random, but there are also many actions there, many options there, because now it will change all the weights between I think minus 1% and plus 1%. But you could also say at random a few of the weights are selected or a certain layer is selected, and it's also not doing crossover at the moment. So there's no 2 best parents combined, for example.
You can also start with like simulating using big situation at the beginning, cooling off.
Yeah. Yeah.
So how many layers does the network have?
1 at the moment. Okay. And the cool thing is with this, because it does not actually train the network, it changes the network and then sees if it's better. Then it's very easy to also change the size of the network. So you can add additional parameters, so it can add a node or it could add a layer and then see if that performs better or worse. You could add it. It's not doing that at the moment. Yeah. Yeah, because those also increase the solution space and that will take more generations. And yeah, it takes more time.
Do they actually have an incentive to drive? Or does that just seem to chill?
Well, within a generation, no, because if they do not drive, they will die.
If you would start it again, would it be?
It will be different because now there's one which was good from the first generation, and that one also outperforms the rest. So it's the rest has less incentive to move. So if I start it again, especially because it only has 10 trains, I will start it in a bit without showing the game, and I will start a larger population, and then you can will just output scores, and then you'll see it's a little bit more interesting than this one. Yeah.
So, do you think this? Have you tried it with like a regular neural network, not using the evolutionary, but just training the neural network itself?
Yeah, and there it becomes very interesting because if you don't give it intermediate scores, then you say, okay, neural net, you're going to take a lot of actions, we're going to give you a lot of inputs, and we're going to accept a lot of outputs, and in the end, we're going to say, yes, you did well, or no, you did not do well. And that makes it very hard to use traditional models. And
you need a policy or something.
There's a problem in reinforcement, right? Because most of the time you just get feedback and you failed.
Yeah. Yeah.
Your program sucks.
Yeah, you cannot say, oh, this was a good action, this was a bad action. You can only say, in general, all of your actions combined, it sucked.
So you're training a neural net with the genetic algorithm?
Yes. Yeah. Yeah.
Have you tried a Q-learning approach?
No, but it's also common in this case and for these kind of games. So that would be very interesting. Yeah,
especially this one.
Yeah. Thanks.
You said that each train had a neural network work with one layer? You mean
One hidden layer.
One hidden
So
layer,
3
yeah.
layers in total.
How wide is it and how well connected is it to the inputs?
It's fully connected, and it has as input nodes it has 5, and it has as hidden layer it has the number of sensors times 2. So if you change the number of sensors, the hidden layer will be slightly larger, and the output layers too. But that's just arbitrary numbers.
Right. Yeah.
So that could also be an optimization, and playing with those numbers would speed up learning or would decrease learning. But then again, that's a problem like this. So you could wrap this in a genetic algorithm to find the best parameters to
Yeah, that's
train.
true.
Yeah.
Before you know it, you lost your job.
Yeah.
Well, so maybe a comment. So if you think these kinds of problems are interesting, you also have the Open AI Gym website, which features a lot of problems like these. Some are simple problems like balancing a pole on a cart. Some are like playing Doom or there's Atari games, and they have very similar setup. So they provide some states that can aid in perceive. They provide continuous rewards that you can use, and then I guess you can just use this algorithm as well.
So the game itself is on GitHub, and you can just, if you look at Laurens Koppenol GitHub, it's called Train a Train. And it just has the game, and you can just implement your own player classes. There's just the human players there, and a naive AI, which is not the AI, but just has the sensors as an example. And from there, it's easy to play around.
What is the substitute?
Yeah, there's
The Netherlands?
Yeah.
Oh, we're seeing inversion behavior.
So when is it cut off?
Yeah, there's time limit, just to speed it up a little bit. But I'll start the one.
We're doing so well.
Yeah, we're almost there.
Almost there.
If I change it, I have to restart it. So that's
just keep it running in the
Maybe
background.
5 million years of train
Yeah, but I think that one is really stuck in local Ultima. Because
like more agents, how would you do that? Like Pygame is not very performant, but 10 is glitchy as hell.
Yeah.
So if you wanted like 1,000 actors in the same setup, how would you implement that?
Yeah, you don't need the graphics. So if you would just implement the rules and you would parallelize the players within a generation, that would speed it up by a lot. And maybe use a different language.
May I suggest using OpenCL?
Is it, what was that? It's for visualization.
It's using GPU as your computation engine instead of your CPU.
Yeah, for the graphics or for the?
No, for the actual evaluation of one.
Oh, nice.
But the big problem here is that you need a CPU to execute the game, right?
What do you mean?
It's not like these are not just only matrix calculations you're executing. You need to actually do some like general programming that is not.
You can use the underlying black-red blue map as the texture and just you can do some.
I think it's
extra.
one of the biggest problems with reinforcement learning right now is that you can't run it on a GPU because you need to, in general, maybe for this game it's possible, but in general you can't use GPU just because the game itself wouldn't run on GPU.
But you would do the training in batches and then you could do the training in GPU.
Yeah, but the training only happens because it evaluates the game, right?
Yeah.
We can talk about this.
You can do it partly on.
Maybe you could do part, but I'm not sure how that.
We can talk about this in a bit. I can show you some really weird stuff you can do with GLSL.
But there are tons of ways to make this many orders faster. Yeah, for sure. Yeah.
What was the reason you chose this combination of algorithms?
I just started making the game, so I could try different things on it. There's many stuff to try, and
this is the first year that I hear about them, but apparently it's very big and it's very diverse and it has a lot of international speakers. I have slides about that. So it's going to happen in May in Amsterdam. The tickets are already on sale. They have a lot of speakers, and I think they published some of their agenda, not sure if all of it. Apparently it's going to take part in 2 days and multiple tracks. As you can see, they have a little bit of everything. And they were kind enough to offer a discount code for the attendees of this meetup if you go to that link. And thank you for coming. As I said, I hope you enjoyed and took home a few lessons, and you are very welcome to come next time.
Thank you.
Yeah.
Special thanks for our hosts, Arno and Julia.
If someone wants to grab a pizza for home, be my guest. Wrap it in for you just like Happy Italy.
And we still have drinks.